Creation, grant this our one request. Help us to build a nation where no man is oppressed. And so with peace and plenty, Nigeria may be blessed. FUNAB Anthem. Thank you very much. Surely, FUNAB, we shall never fail. Once again, we want to welcome you, especially for those of us who have been in this hall earlier today, to the hall once again. You know, earlier today we had the 2025-2026 academic session matriculation, which was a huge success, and the 13th commencement lecture delivered by Professor Shubulola Fasoyiro. But now we are here for another different mission, which is the 107th Inaugural Lecture. But first, before we proceed, permit me to recognize on the seat our Vice Chancellor, Professor Olushola Babatunde Kehinde. Please, a round of applause for the Vice Chancellor. Next to him, by his left-hand side, is Deputy Vice Chancellor, Development, Professor OLAWALE Dairo. We also have on seat the University Registrar, Dr. Titus Adeniyi. You're welcome, sir. We have the Bossa, Mr. Olukayode Oshinuga, and the University Librarian, Professor Abayomi Owolabi. The Chairman, Committees of Deans and Directors, CODA, is also on seat. Please let's welcome Professor Emmanuel Fakoya. You're welcome, sir. We have the Dean of the Inaugural Lecture of today, and he is no one else but the Dean of College, Professor Adebayo Badejo. You're welcome, sir. And the Head of Department of our Inaugural Lecturer, Dr. Fumilayo Alayaki. You're welcome. And most especially, we want to also welcome the man for whom we are gathered here today and now for. I'm talking of no one else but our 107th Inaugural Lecturer, a Professor of Civil Engineering Structures from the Department of Civil Engineering, College of Engineering. Please, ladies and gentlemen, let's welcome Engineer Professor Joseph OLAWALE AKINYELE, who will be delivering the inaugural lecture titled From Waste to Strength, the Power of GEOPOLYMER, Rubberized and Plastic Waste, Concrete for a Concentrate for a Cleaner Environment. Please, another round of applause for him. We also want to welcome his family, led by his beautiful wife, Mrs. Ruth AKINYELE. Professor Adejoke Olukemi AKINYELE. Sorry. Thank you, you're welcome, ma. And the College of Engineering family, we want to appreciate you especially. Please, a round of applause for the College family. We appreciate and welcome our deans and director who are on seat here. Please, let's appreciate them also. And to all the family and friends of Professor AKINYELE, you are highly welcome to this program. Right now, I want to humbly invite the Vice Chancellor for the opening remarks on the inaugural lecture. Please, a round of applause for the Vice Chancellor as he steps forward.
Thank you very much. Please, you may be seated. The Deputy Vice Chancellor, Academic in absentia, the Deputy Vice Chancellor, Development, the Registrar of the University, the Bursar, the University Librarian, the Dean, College of Engineering, other Deans and Directors here present, Head, Department of Civil Engineering, other heads of departments, distinguished members of the University Senate, distinguished academic and professional colleagues in FUNAB and from other universities, all non-teaching staff, all special guests and friends of the university, members of the AKINYELE and Onibokun families, distinguished ladies and gentlemen, gentlemen of the press, great FUNABites. It is my pleasure to welcome you all to the 107th edition in the series of the inaugural lecture of the Federal University of Agriculture, Abeokuta, the second in the Department of Civil Engineering, and the 11th in the College of Engineering. Our inaugural lecturer of today, Engineer Professor Joseph OLAWALE AKINYELE, was born to the family of late Pa Philip Abiodun Ayinla AKINYELE, also known as Baba Soja, and Mama Modupe Ola Olufunke AKINYELE, on the 12th of October, 1971, and he hails from Ota in the Ado-Odo Ota local government area of Ogun State. Professor AKINYELE started his elementary education in kindergarten school at Sabungari, Kano, in Kano State. When his father, who was a soldier with the Nigerian Army, was posted to Akure, in Ondo State, the family initially settled in Ibadan, where he was enrolled at the St. Peter's Primary School, Okiare, Ibadan, in 1977. He later joined his father at Akure, where he attended the Army Children's School, Owina Cantonment, Akure, between 1978 and 1982. He later transferred to the Army Children's School, Letmore Cantonment, Mokola, Ibadan, when his father was posted to Ibadan in 1982. He was admitted to Ahmadiyya Grammar School, Eleyele, Ibadan, in 1984, where he completed his secondary education in 1989. One of his ambitions in life was to join the Nigerian Army like his father. He made several attempts to be admitted into the Nigerian Defense Academy, NDA in Kaduna, but fate will not allow him. He was later admitted to the premier university, the University of Ibadan, in 1993 to study civil engineering during the June 12, 1993 crisis. With the prolonged ASU strike of the 90s, Professor Akinyele eventually graduated in the year 2000. After his Bachelor of Science honors in civil engineering, he proceeded to obtain his MSc and PhD from the same university in 2006 and 2012, respectively. He took part in the mandatory one-year National Youth Service Corps program at the Works and Services Department of Charanchi local government area of Katsina State. He also had his one-year postdoctoral research fellowship at the Tshwane University of Technology, Pretoria, South Africa, between 2015 and 2016. Professor Akinyele is a registered engineer with the Council for the Regulation of Engineering in Nigeria, COREN. His work experience. He joined Ete Aru and Partners, a leading civil engineering consulting firm, Ibadan, after his service for a year's stint before working for some other construction companies. He joined the services of the Federal University of Agriculture, Abeokuta, in September 2007 as a lecturer 2 and rose through the ranks to become a professor of civil engineering structures in October 2021. Professor Akinyele is passionate about teaching and research, and this has resulted in the publication of over 60 research articles in highly reputable journals, referred international conference proceedings, chapter in books, and technical reports. As a professional civil structural engineer, Professor Akinyele has handled many designs and construction works within and outside the university, which included but not limited to the new College of Engineering building complex. He was a member of the College of Engineering team that carried out the reconnaissance survey, location, and the initial design of the Funab Earth Dam at Mawuko, Abeokuta. He was the structural engineer for a group of consultants on the World Bank-sponsored Lagos State Agro-Processing, Productivity Enhancement, and Livelihood Improvement Support, the APPEAL project, between 2022 and 2023. He also led the team for the consultancy of the AFDB-sponsored Akure Water Distribution Network in Ondo State between 2024 and 2025, and many others too numerous to mention. Professor Akinyele has taught several courses like structural analysis, strength of materials, design of structures, bridge design, advanced structural mechanics, numerical methods in structural engineering, finite element methods, hydraulics engineering in the university, and as a visiting lecturer at the University of Ibadan at both undergraduate and postgraduate levels. He was a facilitator in a training program of the staff of the Federal Airports Authority of Nigeria on the design and maintenance of airport runways in December 2022. He has been an external examiner to Covenant University, Ota, and the University of Lagos. Professor Akinyele has also facilitated he has also successfully supervised and co-supervised 5 PhD, over 20 Masters of Engineering programs, and more than 70 Bachelor of Engineering theses, dissertations, and projects. He is a well-trained academic and has attended many trainings and conferences within and outside Nigeria. The latest being the 5th International RILEM Conference on Numerical Modeling Strategies for Sustainable Concrete Structures at the Delft University of Technology, Rotterdam, the Netherlands, in July 2025, where he presented a paper titled Numerical Simulations of the Structural Properties of Geopolymer Concrete Cured in an Aggressive Environment. He also attended a training on smart and sustainable infrastructures at the University of British Columbia, Vancouver, Canada, in September 2023. Professor Akinyele has received awards, recognition, and travel grants from international bodies like Elsevier Publishing Group on the publication of an article that is linked to the United Nations Sustainable Development Goals titled The Use of Polypropylene and Glass Waste in Bricks in 2022. Postdoctoral Fellowship Award of the Tshwane University of Technology, Pretoria, in South Africa, between 2015 and 2016. And the TED Fund Conference Travel Grants in 2010 and 2019. His university commitments. Professor Akinyele has served on various university committees and in other areas of endeavor in the nation, which include but not limited to being the acting head, Department of Civil Engineering, between 2016 and 2018, a member of the Student Disciplinary Committee, Chairman Departmental Curriculum Review Committee, Co-Length Committee on the Mass Production of Bricks, and so on and so forth. His membership of professional bodies. The inaugural lecturer of today belongs to several professional bodies, some of which are the Nigerian Society of Engineers, Nigerian Institution of Civil Engineers, the International Association of Bridge and Structural Engineering in Switzerland, as well as the Society of Cement and Concrete Researchers in Nigeria. And also, in addition, he has been a reviewer for Construction and Building Materials Journal, Journal of Hazardous Materials, Structures, and the Nigerian Journal of Technology of the University of Nigeria, Nsukka. Professor Akinyele's sojourn is not only about structures and engineering. Professor Akinyele is a devout Christian who surrendered his life to Jesus Christ in 1992 and has served in many Christian organizations. He is a committed member of the Ibadan Varsity Christian Union Alumni Fellowship and a minister of the gospel with the New Covenant Church, Bashono Center in Ibadan. Of course, he didn't leave out an area of life which is very, very important. Professor Akinyele is married to Professor Adejoke O. Akinyele of the Department of Forest Production and Products, Faculty of Renewable Natural Resources at the University of Ibadan. The marriage is blessed with 3 God-fearing and wonderful children, Oreoluwa Shalom Akinyele, Oreoluwa Shama Akinyele, and Jedidiah Adeoluwa Akinyele. Distinguished ladies and gentlemen, I have the pleasure to invite Professor Joseph Olawale Akinyele of the Department of Civil Engineering, College of Engineering, to present his inaugural lecture titled From Waste to Strength, the Power of GEOPOLYMER, Rubberized and Plastic Waste Concretes for a Cleaner Environment. Thank you very much for listening. God bless you.
The Vice Chancellor, Deputy Vice Chancellor Academics, the Deputy Vice Chancellor Developments, the Registrar, the Bursar, the University Librarian, the Dean College of Engineering, other Deans and Directors, Head Department of Civil Engineering, other heads of departments, distinguished members of the University Senate, distinguished academic and professional colleagues in FUNAB and from other universities, all non-teaching staff, all special guests and friends of the university, members of my immediate and extended family, distinguished ladies and gentlemen, gentlemen of the press, great FUNABites. I honor and glorify him who lives forever. His dominion is an eternal dominion. His kingdom endures from generation to generation. I praise, exalt, and glorify the King of heaven, because everything he does is right, and all his ways are just, and those who walk in pride, he humbles. Mr. Vice Chancellor, sir, with humility and reverence, I hereby present the 107th Inaugural Lecture of the Federal University of Agriculture, Abeokuta, and the 11th from the College of Engineering, and the 2nd from the Department of Civil Engineering. My journey into the field of engineering was not a mistake, but was greatly influenced by my late father, Philip Abiodun Akinyele, who I respect a lot, a very diligent and hardworking mechanical engineer with the Nigerian Army Electrical and Mechanical Engineering course. I know from the onset that engineering is a tedious and tough profession. But seeing my father bring down and separate the sky engine, PC6 for repairs and complete everything together was very fascinating to me. When I got to Form 3 in the secondary school, my mind was made up to become an engineer and a soldier, coupled with the encouragement from my late father, who really desired that one of his children would take after him both in the military and the engineering profession. My ambition of becoming a military man was beclouded in what was the norm during the military era, to join forces in taking over the government, which was the mindset of a typical barrack boy then. However, God prevented that particular dream from coming to pass in his own wisdom. Mr. Vice Chancellor, sir, finding myself studying civil engineering at the University of Ibadan is a story for another day. Since my graduation from the School of Engineering, my field experience over time, where we design and construct buildings and other civil engineering infrastructure, has opened my eyes to the importance of engineering to human life. As engineers, we are expected to solve the problems of humanity and not to create more. Unfortunately, some, if not most of the materials we use in solving the problem of humanity are themselves creating other problems for our ideal environment. That was why I decided to investigate some byproducts of engineering materials that are sources of environmental degradation and how to remove these impediments. Many engineering materials are used in everyday life. Materials such as cement, concrete, crushed stones, gravels, asphalt, steel from iron ore, timbers or woods, hydrocarbon byproducts like plastic, polyethylene terephthalate, the popular PETs, tire rubbers, and many others are daily used in the construction industry. Most of these materials are obtained in their natural state, but are later converted for use in engineering infrastructure. The process of conversion or production of this material has been a source of concern because some of these production processes have contributed to global warming. The federal government of Nigeria in 2024 started the construction of a super coastal highway from Lagos to Calabar, a distance of over 700 kilometers. The interesting aspect of this road project is the use of cement-based reinforced concrete as the pavement for the highway and other infrastructures. The implication of this is that over 70,000 metric tons of concrete will be used for this project. The concern expressed by experts like Komolafe 2025 on the use of cement-based concrete on this project is its negative impact on the environment. It is believed that about 33 billion metric tons of concrete are produced annually, according to Chechuku 2022, while over 4.4 billion metric tons of cement is said to be produced every year all over the world, according to Shamshin Sori 2020. Greenhouse gas emission from cement production, that is the firing of clinker, accounts for between 5 to 8% of global carbon dioxide emissions, according to HEMA 2021. In the kiln, clay is fired with limestone at a very high temperature to form a clinker, which is later ground into powder. The limestone equation CaCO3, when it is fired, it gives us carbon oxide, which is used for cement, and the carbon dioxide there is released to the atmosphere. This has contributed to the depletion of the ozone layers and the current climate change being experienced all over the world. It was reported that the estimated global greenhouse gas emission for 2021 was 52.8 gigatons of carbon dioxide equivalent. The rapid growth in the production of cement has risen from 2,200 million metric tons to about 3,500 million metric tons in 2020. This is expected to reach 3,770 to 4,400 million metric tons by the year 2050, according to SHA in 2020. What is concrete? Concrete is an amorphous material made of cement, fine aggregates, coarse aggregates, mixed with water. It is the most used engineering materials after water. In 6,500 BC, the Assyrian and Babylonian used clay and asphalt as binders because there was no cement. In 2,500 BC, the Egyptians used lime and gypsum cement for the construction of the pyramids. In AD 1756, John Smithy created the first modern concrete, that's the hydraulic cement. In AD 1824, Joseph Aspidin invented the Portland cement that we are using presently. And in AD 1849, Joseph Monier invented the reinforced concrete, GEOPOLYMER concrete. GEOPOLYMER concrete technology involves the use of natural materials that contains aluminum silicate like calcine kaolin or metakaolin, industrial waste such as fly ash, organic minerals, and blast furnace slag. These materials are mixed in the alkaline environment such as the oxide of sodium or calcium, mixed with sodium or calcium triosilicate in a certain proportion and molarity. Geopolymer concrete was invented by Joseph David Otis in 1979, and countries like Australia and India have accepted the technology, especially in reinforced concrete. Geopolymer concrete does not require the use of cement, and it is not an alkaline activated concrete. The search for sustainable solution has led to extensive research into alternative material for concrete. We have the non-biodegradable materials that are wasting around, materials like the plastic PET, rubber waste, and polyethylene for construction. Also supplementary materials like metakaolin, ground granulated blast furnace, slag, fly ash, corncob ash, etc. are being studied as cement replacement. Implementing the use of these will help us to mitigate the depletion of the ozone layer and reducing land waste. My research contribution. Mr. Vice Chancellor, sir, I wish to state that I have done a lot of works on the use of discarded materials in the production of eco-friendly concrete. My exploration of this route was as a result of my observation as an industry-based engineer who later transitioned into the academic field. My research journey began from observing the indiscriminate disposal of non-biodegradable wastes and the environmental impact of cement production. This led to exploring eco-friendly concrete alternatives. I will speak on only 5 of my research in this area. I will speak about metakaolin as cement replacement, the durability of cement-based concrete in aggressive environments, geopolymer concrete, rubber crumbs and plastic waste in concrete, then plastic and glass waste in bricks. For the metakaolin, AKINYELE et al. 2017 A and B used calcined kaolin as a partial replacement of cement in concrete. Metakaolin, a highly reactive aluminosilicate pozzolan, offers a promising partial replacement for cement. It combines with slaked lime to form compounds similar to hydrated Portland cement. Nigeria boasts an estimated 3 billion metric tons of kaolin deposits across the various states, presenting a sustainable and expanding market for its application in construction. Kaolin is found in commercial quantities in Nigeria with deposits in Ogun, Edo, Plateau, Nasarawa, Katsina, Ekiti, Kogi, Abia, Kano, Niger, Bauchi, Sokoto, Kaduna, Oyo, Delta, and Borno states. The chemical composition of metakaolin, from table 1 above, we can see metakaolin having silicon oxide, aluminium oxide, and calcium oxide, and ferrous oxide. These are the main things that we have in our cement that make it to be cementitious. Our research involved calcining kaolin clay to 700 degrees Celsius and replacing cement with metakaolin at various percentage at 0, 5, 10, 15, 20, 25, 30, and 35% at a 0.5 water cement ratio. For a material to be pozzolanic or cementitious, it must contain 70% of combination of silicon oxide, aluminium oxide, and ferrous oxide, according to ASTM C618. And from the table, we can see that our kaolin and metakaolin met this demand. And the cement, you can see the compound in our cement also, 63.61% of calcium oxide, aluminium oxide 5.64%, and silicon oxide 21.55%. The mechanical test. Compressive and ferrovial test reveal that concrete strength peaked at 20% metakaolin replacement, outperforming the control samples. However, the strength decreased beyond this value. Metakaolin can replace cement at between 20 and 35%. Durability challenge of cement-based concrete in aggressive environments. Mr. Vice Chancellor, sir, the effect of sulfate and chloride ions with the rate of deterioration of concrete in marine environment was investigated by AKINYELE et al. 2018, 2021, and 2024, and IGBA and AKINYELE et al. 2019, 2021, and 2022. The ingress of sulfates and chloride salt into reinforced concrete structures has led to the continuous deterioration of bridge structures and some of the concrete jetties on the Lagos Lagoon. Figure 4 shows the failed pipe caps of some of the bridges in Lagos. When you go there, you see it. Also, corroded steel pipes of some jetties. This is as a result of the effect of chloride and sulfate in the sea water. Now, to predict the deterioration, this research involves submerging concrete cube and beam samples in lagoon water for a period of 1 year, conducting strength tests, and using ANSYS, a software to simulate beam reaction to loading. The mathematical model in equation 1 for the prediction of the strength of concrete was used to determine the strength of concrete submerged in lagoon water and fresh water over a period of time. This model equation was developed by ACI 20992. The results. The grade 30 concrete and 40 concrete samples were cured in lagoon water and fresh water. For the one in lagoon water, they were attacked BL30 and BL40, while the one cured in fresh water were attacked BF30 and BF40 respectively. The result in figure C shows the compressive strength values for all these concrete samples over a period of 1 year. The result clearly showed that the specimen BF30, BF40, and BF30 had increment in strength in the first 90 days, while BL40 experienced a reduction in strength within the same period. However, all the lagoon cure samples relapsed at the end of 365 days. Deterioration rate. The compressive strength results revealed that the deterioration rate within 1 year for BL30 was 0.057, while that of BL40 was 0.044. This indicated that the grade 30 concrete cured in the lagoon water showed a sign of higher deterioration when compared to the grade 40 concrete. This is because of the concentration of concrete in it. This result was used to predict the long-term strength of the concrete cured in lagoon water if the deterioration rate remained constant over the years under consideration using equation 1. We can see some deteriorator sample of the concrete that we cure in the lagoon. You can see how dirty it is, carrying so many organisms on it. Now, using that equation 1, we were able to predict the strength of concrete after 10 years. For the grade 30, the strength reduced to 24.10 millipascal, while for the grade 40, it reduced to 31.11 MPa. This prediction highlights the significant strength reduction over time for concrete cured in lagoon water. We are going to see the reason why now. For the Fleischer's test, BL30 at 90 days had the optimal average Fleischer's strength in all the curing environment. However, this reaction was reversed after the 90th day with a gradual reduction in strength. At this stage, the negative effect of surface salt on the concrete and chloride on the steel reinforcement caused a reduction in strength. Now, we are able to carry out the energy dispersive spectroscopy result in order to know the chemical compound in the concrete. The following elements were detected in the concrete sample cured in lagoon water at the end of 365 days. 11.55% of silicon, 35.3% of oxygen, 40.2% of calcium, 1.2% of magnesium, 6.1% of ferrous, and 5.5% of carbon. There was no traces of sulfur in the concrete sample at the end of 365 days. This was because the sulfate ion has reacted with the calcium oxide and the calcium aluminosilicate in the cement to form gypsum and entry guides. These two compounds, gypsum and entry guides, are the one that causes the expansion, cracking, bond and strength losses with the eventual disintegration of the concrete. We call this spalling. That figure we saw the other time, it is as a result of entry guide and gypsum that was formed. Now, we look at the bond strength test. The bond strength is to determine the bond between the steel rod and the concrete. The result generally showed that PF40 had increased in bond strength between 28 and 35 days with peak strength as 18.6 MPa. PF40, however, behaved differently. The bond strength peaked at 90 with a value of 26.52, but took a downturn to 60.79 at the end of 365 days. The reverse in the bond strength can be linked to the negative effect of chloride that ingress into the concrete and attack the steel reinforcement, thereby allowing corrosion to set in and encouraging the eventual reduction in bond strength. Now, for the beam simulation, we try to look at the behavior of the beams under load. Simulation was carried out to determine the effect of chloride ion on the steel rebar deformation under sustained load at 1 month, 1 year, 2 years, 3 years, and 10 years. The deformation of the bar BL40 at 28 days was 3.78 millimeters and increased to 3.85 at 1 year, 7.41 after 10 years. Meanwhile, the BL40 rod deformation was reducing over time. It shows that it is very good when you compare with the one cured in lagoon water. For the deflection in beam, the deflection decreased from 4.45 mm to 4.13 and from 3.94 to 3.90 for the BF40 and BF30 respectively within 1 year, while it increased from 4.7 to 9.8 and from 3.9 to 32.32 from 28 to 10 years for the BL30 and BL40 respectively. This simply confirms the negative effect of sulfate and chloride ions on the sample cured in the lagoon water. Hence, cement-based concrete resilience is very poor in aggressive environments. Geopolymer concrete. Mr. Vice Chancellor, sir, research has established the fact that the production of cement has contributed about 8% of carbon dioxide emission being released to the atmosphere. One of the alternatives to almost zero production of CO2 in the concrete industry is the use of what is called geopolymer concrete. David Ohit in 2020 was able to compare the energy needs and the carbon dioxide emission of ordinary Portland cement and geopolymer cement during production. He concluded that the production of geopolymer cement will require less 59% energy and 80% reduction in CO2 emission. The effect of aggressive environment on geopolymer concrete was investigated by AKINYELE and Ewetade 2025 and AKINYELE et al. 2025. Samples of geopolymer concrete were cured in lagoon water after 7 days of casting, while the control sample was cured at ambient temperature and were designated as GPCW, that is geopolymer concrete cured in water, and GPCD, geopolymer concrete in dry condition. Normally, reinforced geopolymer beams were subjected to pressure strength tests at while the concrete cubes were subjected to compressive strength at 28, 90, 180, 270, and 35 days in the laboratory. Normally, geopolymer are not supposed to be cured in water because its geopolymerization process will be hindered by water. It is to be oven cured at 60 degrees Celsius or steam cured for quick geopolymerization, unlike ordinary Portland cement concrete that need water during its hydration process for curing. We are able to carry out beam simulation also for the geopolymer concrete. And the result in table 3 shows the experimental result for our geopolymer concrete. For the deflection, for the one cured in water and dry, we discovered that it was observed that the deflection in both dry and wet cured geopolymer concrete were generally low, below 1 mm. When compared to the result obtained for the cement cure, the one we have in the cement based concrete, we are having 3.5, even one was about 32.2 or thereabout. Now, we now look at the cube analysis. The pattern of result obtained in table 4 showed that geopolymer concrete showed an early increase in strength of 80 MPa at 7 days. At the end of 28 days, the GPCD increased in strength to 105 MPa, while GPCW reduced in strength to 45.02 MPa. The sharp fall in GPCW was because of the geopolymerization, which was hindered by the presence of water during the chemical reaction, although it stabilized at 40.90 to 40.01 MPa between 270 and 35 days. When equation 1 was used to calculate the deterioration rates at 10 years, the value obtained was 38.47 MPa, which is greater than the 31.11 MPa obtained for grade 40 of the ordinary Portland cement concrete. We were able to use the stress strain curve to predict the modulus of elasticity, and it was discovered that the modulus of elasticity was between 12.08 and 12.085, which is, this value falls within 10.0 and 20 GPa for cement-based lightweight concrete. Now, we now look at the elemental composition of geopolymer concrete. From table 5, our interest here is chlorine and sulfate, which is the enemy of concrete. Here, GPC samples show high chlorine content when compared to the GPCD. This is due to lagoon water ingress encouraged by the large micropores. But these micropores can be reduced by adequate compaction during casting. For sulfur is consistently low, less than 1%, indicating minimal ion penetration and reduced risk of spalling. The sulfate is unreactive in geopolymer concrete, unlike in normal concrete where we did not find the sulfate because it has reacted. Here it is unreactive. That's why the traces can be found in the sample. GPC is resistant to sulfate. This is an advantage over ordinary Portland cement concrete. This results show that geopolymer concrete has advantage of high strength and are more resilient in aggressive environment than OPC concrete. Rubber crumbs in concrete. Mr. Vice Chancellor, sir. According to AKINYELE et al. 2016, the improper disposal of solid and industrial waste has led to part of the problem that the world is currently battling with. The burning of some of these wastes, such as rubber from tire, has led to the release of poisonous gases such as sulfur into the atmosphere. These gases react with oxygen in the air, which eventually led to depletion of the ozone layers and the formation of gases like sulfur dioxide, which ultimately mix with water during rain to form acid rain, forming sulfuric acid, which is very, very dangerous. Now, we now try to use that rubber crumb in concrete. In a study by AKINYELE et al. In 2016, rubber crumb was used to partially replace fine aggregate in concrete at 0.4, 8, 12, and 16%, and was coded as C0, C4, up to 616 respectively. The material was sourced from Whitefield, a recycling plant in South Africa. This was the work I did during my postdoc in South Africa. This was the research I carried out. The test analysis. Sieve analysis was carried out on the rubber crumb in order to determine the particle distribution, slump test was carried out on the wet concrete, while compressive and tensile strength tests were carried out on the hardened concrete. Microstructure analysis was carried out using SEM, which was used to examine the microstructure of the concrete and the energy dispersive, and this determined the percentage of elements in the concrete. The rubber crumb grading analysis. The particle size distribution curve for the recycled rubber crumb has a steep curve, indicating a type of aggregate containing particles of almost the same size. For the grading requirement, according to ASTM D2487, well-graded concrete must have coefficient of uniformity greater than 6, and coefficient of curvature should be between 1 and 3, and less than 5% fines. From our result, the coefficient of uniformity was 4.5, while coefficient of curvature was 2.0. CC is acceptable, but CU is below 6. The recycled rubber particle is a poorly graded material. For the workability of rubberized concrete, the slump test measure concrete consistency. All the samples showed a true slump, indicating a good consistency. Now, the factor that affected the slump, higher rubber content percentage, lead to the lower slump value between 25 and 10 mm. For the dry rubber crumbs, have a high affinity for water, absorbing it from the mix, leading to drier concrete. By the time we finished mixing, the concrete became very caked, became very hard. That is, we need to add more water to it for it to be good for our work. So for transportation, the water smell ratio may need adjustment to maintain workability. Overall, rubberized concrete maintains acceptable handling and placement. For the compressive strength generally decreased as percentage of rubber crumb increased in the concrete mix. The control strength was 23% higher than the C4 and 35% higher than the C8, while C3 gave the least value, 19.40. Reduction attributed to decrease in adhesive strength between waste rubber and cement. You see that the strength was reducing as more rubber crumb is being added to it. Some would think that is an advantage, but wait to see what is happening. The microstructure was studied. Specimen with rubber crumb showed less dense interfacial zones, micro cracks, and poor adhesion between rubber crumb and cement. Now, the impact of rubber crumb, poor adhesion, a lot of capillary void, micro cracks, and so on and so forth like that. Now, the elemental composition, as more rubber crumb was being added to the cement, so also we have more reduction in the oxygen and magnesium, while we have carbon and sulfur. The increase in rubber content primarily from tire rubber carbon black. This carbon is from the carbon black. The sulfur is for tire because sulfur is used to strengthen the rubber for our tires. So it was detected by the machine. The rubber crumb induces chemical reaction during hydration with high sulfur and carbon acting as impurities. These are impurities in the chemical reaction of concrete. Impurities lead to poor chemical reaction and a reduction in strength. We were able to look at the elemental peak. The elemental peak were between 0.5 and 4 kilo electron volt, showing the dominance of iron, calcium, and oxygen with the traces of the impurity, sulfur, and carbon in all the samples. Now, application of rubberized concrete. What is the code saying about this? For structural limitation, tire rubber concrete with greater 8% rubber may be restricted in structural application due to reducing strength. But according to ACI 213, that's American Concrete Institute 213, it's recommended that 7 newtons per mm square should be good for lightweight concrete, and BSA 210, which we use in Nigeria for our design code, require 15 newtons per mm square for reinforced concrete and 7 newtons per mm square for plain concrete. From our result, the rubber crumb can replace fine aggregate up to 16% in lightweight concrete, because our C16, which is the least, have 19.40, which exceeded the recommended value. That is the catch, because it's greater than what the value, the standard said we should use. Now, we now look at plastic waste concrete. Mr. Vice Chancellor, sir, the improper disposal of the popular plastic bottles made from polyethylene terephthalate has become a nuisance to our environment. According to AKINYELE et al. In 2020 and Harrington 2017, many of these waste generated from this PET material has ended up in the water drains and eventually into the ocean. Some school of thought believe that by 2050, there will be more plastic than fish in the ocean of the world if this trend is not quickly addressed. In fact, sometimes ago, I watched a documentary on BBC where some fish were caught, and by the time they caught it, they find some plastic particles inside the fish. It's so that already we started eating plastic from our fishes. So we have to be very careful the way we dispose of all this plastic. Now, what did we do? The grounded plastic waste was used to partially replace fine aggregate in our concrete at 0, 5, 10, and 15%, and 20%. And the concrete formed from it were coded P10, P0, and up to P20. Now, for the compressive strength, the compressive strength generally decreased as percentage of PET increase in concrete mix. Control sample at 28 days gave us 25.26 newtons per mm square, which was 4.5% higher than the P5 sample. P10 was 40.5% lower than the control. For the P15 PET concentration, the ultimate strength was 20.25, and the P20, which is the highest number, gave us 17.1 newtons per mm square, which is the lowest. This reduction in strength may restrict the use of PET concrete with anything greater than 15% plastic in structural application. Now, we now look at what is the code saying. According to ACI 2 and 3, like I quoted the other time, 7, 15, and 7. And the list we have here is 17.1, which shows that what we have is greater than the recommendation of the code. That is, we can use this plastic waste, but not greater than 15% in our concrete. So lightweight concrete can be used for road curbs, road divider, pedestrian pathways, interlocking pavement, rigid pavement, door and window lintels. The windows of your house, the lintel of your window and house, we can use this plastic waste for it when we mix it with concrete at that percentage. The bending moment was also determined. The bending moment of the concrete beam decreased with every percentage increase in plastic waste. Bricks. Exploring the innovative use of plastic and glass waste in brick production for enhanced durability and environment benefits. This particular research won an award from Elsevier Public Group in 2022 for meeting the United Nations Sustainable Development Goal, SDG 13. The introduction, waste material in brick production. The study investigated the use of crushed glass and polypropylene, that is plastic granules, in 2 sets of fire clay bricks. These wastes were added to bricks at 1, 2, 3, 4, and 5% proportion, and the bricks were fired to 800 degrees Celsius in an electric operated kiln for about 4 hours. The glass infused bricks were designated T1, T2, T3, T4, T5, while those with plastic were designated P1, P2, P3, P4, and P5 respectively. The glass we use is the soda lime glass. The common commercial glass, all these windows, all these glasses, they are made from soda lime. So that when it got broken, we can pick it up and use it for our bricks. Polypropylene plastic, of course, the common plastic often disposed of as waste. Now, there are key performance indicators for our bricks. Number 1, water absorption, which measures durability and internal density. Fire shrinkage indicates dimensional stability and crack prevention. Compressive strength determines material quality and load bearing capacity. And flexural strength assesses bending stress and resistance. When we look at the water absorption of all the samples, water absorption is critical for brick durability. Low absorption indicates a denser internal structure and good resistance to water. All water absorption are below 20%. These are very good. It shows that in water absorption, all of them perform well. For the firing shrinkage indicates how much a brick contracts during firing. Excessive shrinkage can lead to cracks. Here, the control sample was the best, while the plastic infused samples were the worst. Although the general shrinkage were very small and acceptable, the highest was 2.13%, which is also acceptable, by the way. For the compressive strength, which is the main thing. Compressive strength is the critical measure of construction material quality and durability. The glass infused samples are the best, even performing better than the control. When we look at the figure above, the control has 6.15 MPa, while glass infused gave us 11.07, is 11.02 MPa at 5%, but the one with plastic gave us 2.61. Brick classification. Bricks are classified based on compressive strength and water absorption. There are 4 categories of classification of our bricks. The first category tells us that the compressive strength should be greater than 14, but the water absorption should be less than 20%. We can use that one for our external walls and flooring. The second category must have compressive strength greater than 7 and water absorption less than 22% for exterior and interior without plastering. The third category should have between 3.5 and 7 newtons per mm square and less than 26% absorption for ordinary construction, while the fourth category should have compressive strength greater than 15, very low porosity, this can be used for road construction. From our result, the bricks with 2 to 5% glass are in the second category. The one with 0 to 1% glass are in the third category. Plastic bricks with 1 to 3 plastic are in the third category, while the one greater than 3% fall outside the standard classes because of its low strength. We also look at the shear stress of the structure. Now, I want us to look at the microstructure. The impact of plastic weight on brick microstructure. For sample P1 and P5, that is the one that contain 1% plastic and 5% plastic, large voids were observed in the microstructure. The large void was between 23,689 to 95,769 micrometer square for P5, while between 3,068 to 3,083 micrometer square for P1, and the microcrack width of 63.73 micrometer. These large pores and cracks are attributed to the melted plastic. When the plastic melted, it created that void, contributing to low performance and potential weak points. Now, for the glass-infused bricks, for T1 and T5, significant smaller microcracks were observed between 8.96 to 10.70 micrometer for T1 and between 5.89 to 8.17 micrometer for T5. Sample T5 showed the smallest cracks and the highest structural efficiency of 8.01 and 180% greater than the control. This study demonstrates the potential of using plastic and glass waste in bricks. For glass waste, this can be used in board bricks at up to 5% replacement, enhancing compressive and failure strength while reducing water absorption. For the plastic, it is suitable for bond bricks provided the percentage does not exceed 3%, maintaining acceptable strength and shrinkage properties. These findings support the sustainable construction practice by repurposing waste material into valuable building components. I have also worked on the conversion of plastic waste and glass fibers to reinforcement rod using plant fibers as stabilizer for rod. The iron rod the rod we use in concrete. We have worked on it using all this waste also. That is another research. From waste to strengths. Mr. Vice Chancellor, sir. Through my research over the years and this presentation, I have explored the use of innovative materials that are formerly referred to as waste for a greener future in the construction industry. Contribution to human development. My academic journey has focused on human development through teaching, student supervision, and engineering design services. I have taught courses like structural analysis, structural design, hydraulics design, finite element method, theory of plate and shell, numerical method, advanced structural mechanics, and many more at the undergraduate and postgraduate levels. By the mercy of God, I have successfully supervised 5 doctoral candidates, over 20 master dissertations, and about 70 undergraduate projects. Most of my former students are doing fine in the industry and in the academics. As acting head of department, between 2016 and 2018, as HOD, with the support of my colleagues, I was able to establish a design studio for the department, which is currently being used for computer-aided design by our students. I was PG coordinator, exam officer, led the design team for the College of Engineering building complex that is behind us, served in the University Project Monitoring Committee, Student Design Committee, and I've served in various university committees. Conclusion. I've looked at creating a safe environment through recycling of waste material to combat greenhouse gases and ozone depletion. My exploration of alternative eco-friendly materials in the production of cement has revealed that calcined kaolin, or when we fire it become metakaolin, and geopolymer concrete are good substitutes to Portland cement. Waste material like used tire rubbers, polyethylene terephthalate, and waste glass material can partially replace sand, granite, gravels, and clays in the production of concrete and bomb clay in the construction industry. The conversion of this waste material into use in concrete did not seriously have negative effect on the structural properties, especially the strength of the concrete from my research. This research effort align with the SDG 13, the climate action, by reducing greenhouse gas emission, promoting adaptation, and increasing climate change awareness. Recommendation for metakaolin in concrete. I hereby recommend that the partial use of metakaolin in place of cement in concrete, but the proportion of metakaolin replacement should not exceed 20% by weight. Although we can go up to 35%, but for safety purposes, we should limit it to 20% by weight. For geopolymer concrete, I'm recommending the utilization of geopolymer concrete because of its high strength high compressive strength, resistant to sulfate and chloride, and its eco-friendly properties. For plastic waste, I am also recommending the use of plastic and rubber waste as aggregate in concrete, but should not exceed 20% and 60% proportion respectively. For burnt bricks, glass and plastic waste should not exceed 5% and 3% respectively. Part of recommendation: there is a need for increased funding and facilities for research into alternative cement material and waste reuse in construction. Mr. Vice Chancellor, sir, we urgently need a world-class central workshop for the College of Engineering. What we have currently is supposed to be a temporary arrangement. Sir, for us to be able to carry out world-class research and even to generate IGR, we need a central workshop in the College of Engineering. And I know, sir, you are going to heed our call. Thank you, sir. Recommendation: I recommend a strong collaboration between cement producers and research institutions in the adopting pozzolanic material. There is a need for the enactment of legislation for the appropriate recycling of non-biodegradable waste for concrete production. Acknowledgement. Mr. Vice Chancellor, sir, this presentation is a heartfelt expression of thanks to the many individuals and institutions who have shaped my life and career. It is a testament to the power of faith, family, mentorship, and community. I want to thank my Lord, my God, and the Savior of my soul, Jesus Christ, the immortal, invisible, and the only wise God, the author and finisher of my faith, who has preserved my life up to this moment. In the course of my journey of life, I have traveled and passed through the shadow of death, but God has kept me alive to see this wonderful day. To him be all the glory, honor, and adoration. This journey has been marked by divine preservation and guidance, for which eternal gratitude is offered. My pillar of upbringing, my father, Baba Soja, Pa Philip Abiodun Akinyele, a disciplinarian to the core, a real soldier man, a lover of education. He ensured that all his children receive the best possible schooling. Despite his own limited opportunity, his dedication to learning, even within the Nigerian Army, was a profound influence on me and my siblings. My mother, Mama Mojugola Olufunke Akinyele, God bless you, ma. Her unwavering belief and encouragement were crucial during my early academic struggles. I was a slow starter, but she was always behind me. Her support transformed moments of shame into opportunity and growth. To my Vice Chancellor, Professor Obi Kehinde, I became a professor under you, and you gave me this opportunity to present this lecture. I am very grateful, sir. Professor O.O. Balogun employed me as a staff of this university. Professor Obi Oyole appointed me acting HOD of Civil Engineering Department and granted me the post-doctoral leave to be at TUT in Pretoria, South Africa. Under Professor Enukweme, I also served as acting HOD. Professor F.K. Salako promoted me to the position of a reader. A special thanks to all past and current Deputy Vice Chancellor, Professor Olukayode Akinyele, DVCA, who was my chairman when I served in the Student Design Committee. Thank you very much for your leadership. And my immediate past dean, Professor O.U. Dairo, DVC Development, who was my immediate past dean. He was the one who submitted my name for this inaugural lecture before he was elevated as a DVC Development. Thank you very much. I want to appreciate the registrar, the bursar, and the university librarian. The past principal officers are my esteemed professional colleagues and friends in the College of Engineering and all other colleges in Funab. I have to mention my Oga, Professor O.S. Awokola, the foundation HOD of the Department of Civil Engineering. God bless you, sir. And my dean, my current dean, Professor A. Badejo, who is also a very good friend of mine. My HOD, Mama Sivu herself, Dr. Ms. Fumilayo Alayaki. Thank you, I appreciate you. To the college family, you are too numerous to mention. I want to appreciate every one of you. All former deans, all former HODs, current HODs, colleagues, I appreciate you. And some of my friends who are outside the college, I appreciate everybody. Your collaboration and support have been invaluable throughout my career. I want to appreciate my mentors. During my postdoctoral research, Professor W.K. Kukolati, R.S. Wanjala, and J.N. Ndabuke, we lost him just about 3 weeks ago at Shrine University of Technology. Also a co-researcher of mine, Professor Bababemi Adewumi at Stellenbosch University, who recently hosted one of my PhD students in his laboratory. I appreciate every one of you. The University of Badon, the Vice Chancellor of the University of Badon and his team, for approving my visiting lecturership in that university. To my HOD in civil engineering, Professor G.M. Ayinola, I appreciate you. My undergraduate supervisor, who could not make it there, Professor A.O. Koka, I appreciate you. I'm the late Dr. Gabriel Ayodele Alade, my MSc and PhD supervisor. Baba taught me structures. Some years ago, I was teaching structures, and one of the students asked me, said, which textbook are you using? We didn't think I said G.A. Alade. Baba taught me structure, and I pray his soul will continue to rest in peace. And all other teachers of mine, Professor Agbede, thank you, I appreciate you. All other teachers of mine and my colleagues in the Department of Civil Engineering, University of Ibadan, I appreciate you. The Dean, Faculty of Technology, Faculty of Law, and all other deans from University of Ibadan, all the staff of faculties of technology and renewable natural resources, I appreciate every one of you. My mentor, unfortunately, he could not make it here today, Professor Jacob Olorunjuwon Akinyele. He influenced my transition from industry to academics. I remember whenever I go to his house when I was in the industry, he would ask me, Wale, when are you going to do your master's? He encouraged my obtaining the master's degree. In fact, there was time he said I should go to FUTA, go and get the form. He pushed me because I was reluctant. So he encouraged me to take my master's form, and my career path changed. Thank you, sir, for seeing the future and encouraging me to forge ahead. To my classmates, the UI Civil Engineering Class 2000, the class of thinkers. How do I say it's the class of thinkers? In that class, we are just 37. Apart from those who are in the industry, who are doing well in the industry, that class of 37 are 4 professors. Myself, my current dean, Professor Badejo, Professor Ajagbe, I'm sure he's there, and one of us, Professor Sheon Kolade, is a professor in United Kingdom. So he's a class of thinkers. Also, the UI Millennium Tech Sets, members of the Society for Cement and Concrete Researchers in Nigeria, led by Dr. Olonode, I hope he's there. Also, I want to appreciate the CERECOM, the Ceremonial Committee, for your effort, the Population Committee, and the ICT team for your support. I want to thank you all. For my spiritual foundation, the Ibadan Varsity Christian Union, the IVCU, that's the way we call ourselves, and the Alumni Fellowship. They played a pivotal role in my spiritual growth, shaping my understanding of Christianity and the Christ-like virtues. Now, when AKINYELE says no at times, when you think I'm stubborn, I'm not stubborn. I'm only swallow what I was taught. Praise the Lord. Thank you to the president and members of the fellowship. When I was in IVC, I have some prayer partners. From my 100 level, we normally pray together. One of them is there, Pastor Debo Adeshino. God bless you. And some others like that. We are prayer partners when we are at the IVCU. Now, my pastor at the New Covenant Church, Bashorin Ibadan, Reverend Dele Adeyemi, and all the elders, the Nobles and Palace Daughters Club of that church, members of the congregation for their spiritual guidance and the support. I want to thank you for giving me the platform to fulfill my ministry. We will not lose our rewards in Jesus' name. My extended family, the Onibokun dynasty. My in-laws, the Onibokun dynasty of Iwoye-Ijesha, have been a source of immense support and love to me. My father-in-law, late Prince Adokege Emmanuel Onibokun, he was my second father after my biological father, a loving and very accommodating old man. And my second mother, Mama Janet Biduni Onibokun Yeye, a true mother to me. God bless you. I pray for good health for you. To the Jebutus, Adura Migas, Akinyemis, Ojurongbes, Olanipekuns, Folorun Shores, and Auntie Tolu, I call her Sholu. Thank you for being a loving family and pillar of support to me. I appreciate every one of you. To all my cousins, both from the Ajibose, Adetuji, and Rufai family, I want to thank you. To my siblings and their children, Mr. Ezekiel Olaleke Akinyele Egbonbosa and his wife, Auntie Ruth. Mrs. Abosede Bangbade and her husband, Uncle Yomi. Olayinka, the baby of the house, Esther Shenraji and her husband, Mr. Shenraji. I want to remember 2 of my siblings. The lowest time of my life was when I lost 2 of my siblings within the space of 1.5 years. Ms. Oluwayemisi Christiana Akinyele and Olakunle Benjamin Akinyele, who was my roommate in the university before he moved to UCH as a medical student. I know they passed away. I know they are with the bosom of the Lord. I remember them and I thank God for their life. And to my children, Ore Oluwafie Yijimi Shalom Akinyele, who was my batmate. She's a lady geologist. And my second daughter, Ore Olaoluwa Shubebi Shama Akinyele, the lady engineer. She studied civil engineering like her father. And the man of the house, Jedediah Ajoluwa Akinyele, Mr. Liverpool, you will never walk alone. My lovely family. Now, to the bone of my bones, counselor, confidant, editor-in-chief, gist partner, prayer partner, soulmate, a virtuous man to the core. You have made me to be known in the gates. When I sit among the elders, your children rise up and call you blessed. I praise you. You have done well and excel. You are beautiful in and out. You fear the Lord and you are blessed. My sweetheart, Professor Adejoke Olukemi Akinyele, I love you and God bless you. And to the King eternal, immortal, invisible, the only wise God, be honor and glory forever and ever. Amen. I want to thank you all.
Please, you may have your seat. You may have your seat. Thank you very much. So, now you know that when they keep increasing the price of cement, there's an alternative. Distinguished guests, ladies and gentlemen, we want to thank and appreciate Professor AKINYELE J.O. for delivering this thought-provoking and wonderful inaugural lecture. Congratulations, sir. And the Federal University of Agriculture, Abeokuta, presents this award of honor to Engineer Professor Joseph OLAWALE AKINYELE of the Department of Civil Engineering, College of Engineering, as the 107th Inaugural Lecturer of the University, dated this day, 19th November 2025. Congratulations, sir. And then on behalf of the university, I also present this to you. We present this to you as a token of what we do in the university. Thank you very much. Congratulations. So you may take this. Distinguished ladies and gentlemen, we want to appreciate you for being good listeners at this 107th Inaugural Lecture of our university. But before we go, yes, the inaugural lecturer has done a good job by acknowledging and appreciating all of us. I just want to cap it up by once more appreciating a few people amongst us. Thank you for coming, and thank you for being part of the 107th Inaugural Lecture of our university. First on the list, I appreciate the spouse. He has mentioned all that she is, and I don't need to go over them once again. Professor Adejoke Olukemi Akinyele. Madam, you are welcome. She's the Dean, Faculty of Renewable Natural Resources at the University of Ibadan, Oyo State. She's the wife of the inaugural lecturer. We also have in our midst, and I want to appreciate them for coming, though it's their day, Oreoluwa Akinyele, the daughter. You are welcome. And also, Adeoluwa Akinyele, the son. You're welcome. Of course, I would like to also specially welcome and congratulate the mother of the inaugural lecturer, Mama Modupe Akinyele. Mommy, congratulations, ma. Eku orire. Oju yin a tubo ma rire. It's a thing of joy. It's a thing of joy for her. You have done a good job, and you are seeing the product today. Congratulations, Mama. We also want to thank and welcome Mrs. Ruth Akinyele, the sister to the inaugural lecturer. Mrs. Ruth Akinyele, thank you, ma. You are welcome. And the husband, congratulations. Mrs. Sheunrai Olanyinka, also the sister, you are welcome. And Mrs. Bose Bangbade, she's also here. You are welcome. Congratulations to the family. We also have Dr. Sunday and Dr. Mrs. Adetumbi Akinyemi, who are in-laws. Dr. Sunday Akinyemi was my classmate in UI. You are welcome. I won't call you the name we used to call you. Dr. Adura Migba Modupe Adefoyeke, the sister-in-law. You are welcome. Mrs. Abiodun Olubamiwa, the aunt. You are welcome, man. All guests from Ibadan, we welcome you. We appreciate you. University of Ibadan, the church in Ibadan. Thank you for coming. We appreciate you for joining us. College staff, we appreciate you. Okay, stand up for recognition. The former Vice Chancellor, Landmark University is there. See them in the Egbe Joda. I also want to thank and appreciate our Egbon here, retired but not tired, the foundation HOD of the Department of Civil Engineering. Egbon, Engineer Professor Awukola, OS Awukola, you are welcome, sir. Thank you very much. Please have your seat. And all deans, directors, members of Senate, every staff that have attended this. Please, we will thank you very much. God bless you real good. Thank you, and God bless you.
Please let's appreciate the Vice Chancellor once more. Indeed, it's a thought-provoking lecture by Professor AKINYELE. Thank you very much, sir. And a quick takeaway for me, I think henceforth all the plastic bottles that I waste throw into the incinerator at home, I'll keep them. Maybe one day, as my VC said, it will be alternative for cement for me. Next, before we call it a day, please permit me to take this quick announcement for all the college staff and students that are here. You are to come to the college for your entertainment. All the guests of the inaugural lecturer are also to go to the College of Engineering boardroom where they will be entertained after the lecture. Then all the non-teaching staff to take the exit B by my left-hand side and the teaching staff to take the exit A by my right-hand side, while all the students are to remain at the gallery inside the hall. So right now, we want to appreciate you once again for making it a day with us here in FUNAB for the 107th Inaugural Lecture. We will take the anthem in reverse order, which is FUNAB anthem first, then we recite the pledge. After that, the procession files out in reverse order also through the center aisle. So please may we rise for the FUNAB anthem.
We
pledge. I pledge to Nigeria, my country, to be faithful, loyal, and honest, to serve Nigeria with all my strength, to defend her unity, and uphold her honor and glory. So help me God. So please let's remain standing while the procession files out in reverse order. We want to appreciate you for making it to the Federal University of Agriculture, Abeokuta, for this 107th Inaugural Lecture of the University, delivered by Engineer Professor Joseph OLAWALE AKINYELE. We appreciate you, all the college family, and let me remind you, if you are not on Ankara, no semo for you, for all the college families. So please, go Ankara, go Jesemo. So we want to urge all our special guests of the inaugural lecturers, to want to move to the college building where they will be entertained, especially by the inaugural lecturer, while others should stick to the announcement as announced earlier. We appreciate the beautiful wife, the beautiful and amiable wife of our inaugural lecturer. We say thank you, and the family, all the other family members, we say thank you very much for being here today. Our ceremonial committee members, we appreciate you also for putting up another successful event. In fact, today is a combo for the ceremonial committee, and it's a success. We appreciate you, especially the leadership of the committee, Professor Temitokwe Ajadi. Thank you very much for organizing the team properly. And to all Funabites, we say